Let's take a look at modern atomic theory. What we're going to do is we're going to take a look at modern atomic theory, and then we're going to go through what is covered in Unit 2. This would be atomic theory, obviously, subatomic particles, including electrons, protons, and neutrons. We'll also discuss electron configurations, and we'll end with a little sprinkling of nuclear chemistry and specifically nuclear decay. So for modern atomic theory, first thing that you need to know are Dalton's postulates. Dalton has 4 postulates. His model of the atom is quite simple, just a ball, but atoms are indivisible, all atoms of an element are identical, atoms combine to form compounds, and atoms are rearranged in reactions. Now, several of these postulates are thrown out the window pretty quickly. Atoms are indivisible. We know that atoms are divisible because there are protons, neutrons, and electrons. With J.J. Thomson's CRT, cathode ray tube experiment, he did this experiment in 1897 and found that, hey, there's these electrons in the atom, and had to revise Dalton's model of the atom. He came up with the plum pudding model, placing negative electrons within the atom. After J.J. Thomson, rolls in Ernest Rutherford. Ernest Rutherford performed a gold foil experiment where he used alpha particles to bombard a piece of gold foil. The nuclei in that gold foil sometimes deflected the alpha particles and sometimes bounced back the alpha particles from their original direction. Most of the alpha particles passed straight through the gold foil, which just so happened to be a few atoms thick, unaffected, and they were detected on the outside of this screen, this zinc sulfide screen. Most of them detected right here, a few of them detected other locations. From his experiment, what Ernest Rutherford found was that the nucleus is extremely small. Most of them pass through unaffected. It's extremely dense because these alpha particles are very, very heavy, and the only thing that could bounce them backwards in the direction that they came is something extremely dense. So the nucleus is very small, very dense, and is positively charged. As some of these alpha particles were deflected just a small amount. Alpha particles are helium nuclei, which means that they are it contains 2 protons and 2 neutrons. So an alpha particle is positively charged. And so sometimes these alpha particles that were deflected were just deflected because of protons in the nuclei of the gold foil and the charge, the positive charge of the alpha particles.
Let's take a look at protons, neutrons, and electrons. What we'll do is we'll pay attention to their location, their mass, their charge, and when they were discovered. Pause the video here and jot this down. Now, let's investigate a symbol. In the upper right-hand corner, that exponent is the charge, +2 for magnesium. In the upper left-hand corner, there's the mass, 23. And in the bottom left-hand corner, there's the atomic number, 12. The formulas allow us to calculate the atomic number, the mass number, and the charge. Watch as I go through this. Now take your time and repeat this process.
Let's investigate electron configurations as they progress across the periodic table. We start off with 1s, followed by 2s, followed by 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, 4f, all the way to 4f14, and then back to 5d, 6p, 7s, 5f, 6d, and 7p. Let's figure out how to set this up on a new periodic table without having these codes already written for us. Notice this is the S block, and the coefficient starts with 1 in the S block. With the P block, the coefficient starts with 2. In the D block, our coefficient starts with 3. And in the F block, the coefficient, the energy level, starts with 4. So we start with 1, 2, 3, 4. The letter describing the shape of the orbital, the electron cloud, S, P, D, F. Our exponent, which tells us the number of electrons, always increases as we go from left to right. And it starts over in each period, in each row. So we got 1, 2, 1, 2, 1, 2, 1, 2. 1, 2, all the way to 10, 1, 2, all the way to 10, 1, 2, all the way to 6, and 1, 2, all the way to 14. So let's set it up on a normal periodic table. Remember, this is our S block. So we would start with 1 S. This is our P block. And we start with 2 P. This is our D block. And we begin with 2 D. And finally down here we have our F block. And we start with 4 F. I believe I said that was 2D. It should be 3D. Don't make that mistake. Remember, it's 1S, 2P, 3D, and 4F. The exponents go from 1 to 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1, 2, 3, 4, 5, 6, and 1 all the way to 14.
Next, let's construct electron configurations, orbital diagrams, and noble gas notation for bromine with 35 electrons. First, let's locate bromine on the periodic table, and then identify every element at the end of each block until we get to bromine. Next, let's go ahead and write down the electron configuration. We start with 1s, 2, followed by 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p5. You can pause the video now to write it down. With an orbital diagram, we're going to show that same electron configuration as arrows. These arrows denote the spin of the electrons. We should be placing one electron in each orbital, each blank, first before plugging in the second one. The arrows will cancel spin. Check to see if I made a mistake here in 4p. With noble gas notation, it's quite simple. Look for the noble gas, argon, before the element bromine. Put argon in brackets, and then add on the next three pieces. In this case, 4s2, 3d10, 4p5. Stop the video one more time to catch up. Let's take a look at the rate of decay of a substance. A half-life is the time it takes for 1/2 of a substance to decay. We can figure this out, T1/2, on a graph. If we notice that the initial mass is 100 grams, half of that would be 50 grams. So we locate that on the graph and drop it down and see that it took 30 minutes for half the substance to decay. How much decays in 2 hours or 120 minutes? We can see from the graph it's about 5, but let's do some math. Divide each by 2, and eventually we'll find that 6.25 grams remain. However, this is how much remain, not how many have decayed. How long would it take to reduce the mass of a 200 gram sample of the same substance to 25 grams? To do this, we would have to go from 200 grams to 25 grams. Let's investigate. 200 to 100 to 50 to 25, dividing by 2 each time, would lead us to 3 half-lives. If there are 30 minutes for each half-life, then 3 half-lives would mean It would take 90 minutes.